Swayam Prabha. Digital India. Educated India.
So now we will look at the Reynolds flow model, which is an algebraic model, as we said earlier, unlike the Stefan flow model, which is a differential equation model, but a one-dimensional differential equation model, and the Couette flow model, which again was a one-dimensional model. Our interest now is to develop the features of the Reynolds flow model. And what I will do is first of all define Reynolds flow model again, go over the Reynolds flux hypothesis. The Reynolds flow model is supposed to mimic the boundary layer flow model. We will also consider momentum transfer with suction and blowing. We will also consider single phase convective heat transfer with suction and blowing, and then the four types of mass transfer problems in which the species mass transfer equation as well as the energy equation will be invoked. I am now going to define the Reynolds flow model. As you recall, this is the interface, this is the considered phase to which the mass transfer NW is taking place. This is the transfer substance phase from where the mass transfer is taking place to the considered phase, and this is the infinity state, which is far away from the interface in the considered phase. So, the principal idea of the Reynolds flow model revolves around postulation of a fictitious flux. It is a notional flux, kilograms per meter square second. So, it is a notional mass flux defined in the infinity state, and its direction is towards the interface. And in doing so, as it flows from the infinity state towards the interface or the W state, it carries with it the properties of the infinity state. So, that is the first postulate of the model, and the model develops algebraic relations that are related to the real transport phenomena by reference to this flux G, and further the model will result into NW equal to G times B. So, instead of the logarithmic relations we saw earlier, the model will develop NW equal to G times B as the appropriate relationship. Now, the objective of course, in order to solve the problem, we first need to define B, of course, which we have done in the previous two lectures for a variety of mass transfer problems. And the second thing is to evaluate G, but the way we will do it is our route will be that G will be related to the value of the heat transfer coefficient in the absence of mass transfer. So, we are going to relate G to heat transfer coefficient for VW equal to 0. And the reason we do this is because these values are available for wide variety of situations through correlations. So, given a mass transfer situation, let us say flow over a cylinder like this, then I would know what the Nusselt number is as a function of Reynolds number and Prandtl number, Nusselt number based on diameter d. I would know what it will be as a function of Reynolds number and Prandtl number, and for which I can divide H of VW equal to 0. If I can relate this value to G, which is in kilograms per meter square second, whereas H is in watts per meter square, or essentially joules per meter square second. So, obviously, we expect a relationship between G will be proportional to H coff VW equal to 0 divided by specific heat. Now, this will have the same units because H coff is joules per meter square second and Cp is joules per kg per Kelvin divided by meter square Kelvin, K divided by K divided by K. So, K gets cancelled, joules and joules get cancelled, and again you will get kg per meter square second. So, this is really the this is what we are aiming at. This is what we are aiming at. What therefore, this will do is the following, that given a mass transfer situation, of any kind, this can be a mass transfer flow over a cylinder, or it can be flow through a tube or anything like that. We calculate the appropriate value of B and evaluate G from the knowledge of the heat transfer coefficient in the absence of mass transfer in that same situation. So, basically no differential equations are solved, the entire model is algebraic. Now, in order to facilitate further discussion, I am going to define in the W state two more surfaces which are almost coincident with the W interface. One of them is the TW state, which is just inside the considered phase, and TL state, which will be just inside the transferred substance phase. So, this is what TW and TL are. In the T state, as you remember, there are no temperature or composition gradients, and because they are uniform. In addition, we shall also postulate that there will be conduction heat transfer from the considered phase to the W state, and there can also be possibly some temperature variation from deep inside the transferred substance phase to the interface, in which case there would be some conduction heat transfer even in the transferred substance phase, which I have called QL. This is QW in the considered phase. There can also be radiation heat transfer to the wall in the considered phase. And in this model, for convenience, we will account for it as though the radiation flux actually penetrates the interface and appears in the transferred substance phase. The reason for doing this would be very obvious as we go along. So, there are a few new definitions introduced: TW state, TL state, heat flux QW and heat flux QL in the considered and transferred substance phases respectively, and the Q radiation, which is accounted in the transferred substance phase. The mass transfer flux is the sum of all species transferred across the interface. So, NW can be sum of NJW, let us say in the transferred substance phase, and NKW in the considered phase. The species J in the transferred substance phase need not be the same as species K in the considered phase. This is typically the case when, let us say, I have a mass transfer taking place across a wood particle. Then here there will be the wood itself has a formula of Cx Hy S HO P S Q and so on and so forth. And when the wood burns, for example, you will get all sorts of gases like CO2, CO or H2, depends on the temperature of the surface. So, the species involved inside the wood surface need not be the same as involved in the considered phase, but the sum of those fluxes of these species and the sum of the flux of these species should be the same. We say QW is positive when flowing towards the interface from the considered phase, and QL is positive when flowing away from the interface in the neighboring phase. So, in other words, in this figure both QW and QL are shown in the positive direction. If I now draw an interface, say WW, and let us say this is TW and this is TL, there is QW here and QL in this direction, then the mass transfer flux is passing like this NW. So, if I take the control volume like this, then NW into HTL, which is coming in, plus QW, which is also coming in, must equal what is going out, which is QL plus NW into HTW. So, NWT THTL comes in, and what is going out is NW HTW. That is what we mean. And therefore, you will see that QW minus QL would be equal to NW into HTW minus HTL. Therefore, QW minus QL will be NW times HTW minus HTL, where HTW and HTL are enthalpies of the transferred substance at the TW and TL state. This is very, very important. HTW simply implies the enthalpy of the transferred substance if it was to appear in the considered phase as HTW. HTL, on the other hand, is the enthalpy of the transferred substance in the neighboring phase, but at the temperature of the interface. So, that is what we mean by enthalpy here. So, suffix TW and TL are different from suffix W itself. Suffix W refers to the mixture enthalpy, whereas suffix TW refers to the transferred substance enthalpy, both in the W and L states. That is just inside the considered phase and inside the transferred substance phase. Now, if QW minus QL is not equal to 0, then a phase change occurs. For example, if HTW minus HTL was equal to the, remember HTW is the vapor phase, for example, in an evaporation problem, and HTL will be the liquid enthalpy, then HTW minus HTL would be simply HFG, the latent heat of evaporation, and therefore, QW minus QL will not be equal to 0, and that is where when the phase change occurs. So, that is the idea of why we define HTW and HTL as the enthalpies of the transferred substance in the vapor in the considered phase and in the transferred substance phases. QRAD from the considered phase to the interface is positive, it is accounted in the neighboring phase. So, with these definitions, we now turn to the main hypothesis of the model. Now, in different applications with or without chemical reaction, complex processes occur in the considered phase. That is where you will have effects of property variations, effect of turbulence, and variety of other issues. There may be chemical reaction, there may not be any chemical reaction, so on and so forth. This sort of situation would require solution of the complete set of boundary layer equations. And what the algebraic model or the Reynolds flow model tries to do is to say that to avoid solution of any differential equations, it is assumed that the complex processes can be effectively simulated by a fictitious flux G through the infinity state towards the interface, carrying with it properties of the infinity state. In other words, G flux carries with it the properties of the infinity state toward the interface. On the other hand, NW plus G flux carries with it is again postulated at the infinity state, but it carries with it values of the W state, values of the upstream values, if you like, likewise upstream values here in this direction. This is a very important distinction between the two fluxes defined. that G flux carries with it the properties of the infinite state as it moves towards the interface, whereas N w plus G moves away from the interface and carries with it the values of the W phase, W state. So, that is what I have said, a fictitious flux N w plus G through infinity plane away from the interface, carrying with it properties of the W state. Now, what this ensures is that in the considered phase, there will be no net generation of mass at all, because G is coming in and G is going out. So, there is no net generation of mass, and that is what is expected even in a real boundary layer flow. There should be no net generation of mass. The magnitude of G is not affected by the presence of gradients of omega j, T or turbulence, radiation, etc. in the considered phase. So, that is another characteristic of the G flux. It is also not affected by the direction of N w. In other words, I may have a problem of evaporation in which N w is this way, I may have a problem in which condensation occurs in which the N w is negative. So, G is not influenced by presence of by the direction or magnitude of N w, and secondly, it is not affected by gradients of omega j, temperature or turbulence quantities in the considered phase. And yet, in spite of these assumptions made, the G flux is supposed to produce the same effect at the interface that the real boundary layer flow is likely to produce. This is the claim of the model. This is the claim of the hypothesis, that it can in fact represent all effects of a real boundary layer flow, although the method is very simple and algebraic. To illustrate this, let me consider the case of evaporative cooling. So, for example, let me say that I have a very hot surface here at temperature T s, and it is hot because very hot gases are flowing over it in the infinity state. Very hot gases are flowing and they are dry, very little humidity. Obviously, to protect this surface from the hot gases and to keep its temperature down, what one might do is to provide, let us say, a water film here, pass a thin film of water. Then what it will do is that the water film will evaporate, and in the process will receive heat both from the solid surface as well as from the hot gases. So, this is the likely temperature profile. Remember, in the absence of the film, probably the temperature would have been much higher than what is shown here. So, in order to cool down, but at the liquid film, the temperature will drop considerably, and that would result into actually some transfer of heat through the liquid film, from the wall to the film, to the edge of the film, and likewise there would be heat transfer. So, Q w in this case would be positive, but Q L, which would be now in the from the transfer substance phase to the interface, would be negative. Q L would be negative, and N w would be positive. So, what we expect, therefore, the Reynolds flux hypothesis states that a G flux of hot gases towards the interface, together with the N w plus G fluxes of cooler moist air away from the interface, hot gases towards the interface, will produce the effect that N w is greater than 0, Q w is also greater than 0 because it flows into the surface, and Q L will be negative because it is also flowing into the surface from the neighboring phase. Now, this is what we expect the real flow to do, and the Reynolds flux model claims that it will do precisely that, So, in this sense, the G flux is considered capable of responding to the mass fraction and temperature gradients as well as turbulence effects in the considered phase, as shown in this figure on this side. So, it disregards what the temperature gradients here are, what the temperature gradients here are and so on and so forth, or the mass fraction gradients here are, because remember mass fraction gradient would fall. It disregards any turbulence effects in the considered phase, and will produce exactly the same effect, N W greater than 0, Q W greater than 0 and Q L less than 0. That is the claim of the model. Let us see how we can justify that. Because it can handle both momentum and heat transfer, we are going to consider the control volume between infinity and W states. So, basically what I am going to do now is to consider the W state and infinity state, and I am going to consider momentum transfer. Then the G flux will bring with it G times U infinity. So, momentum in will be G times U infinity. Momentum out will be N W plus G U W, N W plus G U at W plus shear stress tau W. That is also momentum out of the cell, but at the surface U W will be 0, therefore, that goes out. So, basically if I equate the two, I get G U infinity equal to tau W. That is what the Reynolds flow model implies. So, let us see what does this mean. Well, so basically as you will see here, I have set N W plus G U W equal to 0, and therefore, G U infinity divided by tau wall would equal 1 and N W divided by rho times V W. Yes. So, what I have done here is 1 is equal to N W itself is rho V W. So, I am replacing 1 by N W by V W, or N W can be written as G times rho V W U infinity by tau wall. That would be equal to G into V W divided by U infinity, tau wall over rho U infinity square. Essentially, I have divided and multiplied by U infinity. And what is this quantity? This is essentially V W by U infinity divided by C F x by 2, and therefore, N W is simply G times B F. Our claim that the model is able to predict all effects of momentum transfer through this expression N W equal to G B is verified as long as we interpret B in this fashion, B F equal to V W U infinity divided by C F x 2. So, in order to get G, what will be G? The meaning of G will be tau wall over rho U infinity, which will be rho U infinity C F x by 2. So, in the momentum transfer problem, G would be simply rho U infinity C F x by 2, and C F x by 2 is available to us from correlations for many problems. Let us look at single phase convective heat transfer, in which they consider the CV between T and infinity states. So, now what I am going to do is to consider this is the W state, this is the T state, and this is the infinity state. Then you will see that heat in will be G times H infinity. There will be N plus W, N W plus G, H W, and there would be here N W times H T. This is the, so I am considering the control volume between infinity and T T states. So, there is it will bring with it G E H infinity as the total energy flux. There will be N W into H T will be the total energy flux coming in here also and here, and what will be going out is N W plus G H W, and that is going out. So, if I equate what is coming in and what is going out, then you will see that I get this relationship. Rate of heat flux in is equal to G H infinity plus N W H T plus N W plus G divided by multiplied by H W. So, if I equate and rearrange, then again you will see I get N W equal to G times B H, where B H is equal to H infinity minus H W divided by H W minus H T, or H infinity in this case, because it is a single phase mass transfer, single phase convective heat transfer with suction and blowing maybe. This will be simply C p into T in the infinity state minus C p into T into W state divided by C p T W state minus C p T in the transfer substance phase. And therefore, N W will be equal to N W V W. If the specific heats are equal, of course, B H would be simply T infinity minus T W divided by T W minus T T. If I now consider infinity state and W states, so if I now consider those states, then you will see here you will get N W H W. So, my equations would now read as G H infinity coming in, N W H W coming in, and N W plus G H W going out. So, that is what I have written, plus there would be Q W also, which will go out between in this control volume for this control volume. So, you will see that I get rate of heat flux in as G H infinity plus N W H W, rate of heat flux out will be N W G H W plus Q W. And if I equate and rearrange, then I will get G is equal to H times Q W divided by H infinity minus H W. And if specific heats are equal in the infinity and W states, then G would be simply Q wall divided by C p T infinity minus T W. And as you know, this would be simply minus H cof V W by C p. So, therefore, G is indeed related to heat transfer coefficient in the presence of suction and blowing. So, that is what the single phase convective heat transfer shows. Convective momentum transfer shows that G is equal to rho u infinity C f x by 2, and here H cof is equal to the. Now, you can see very well that if I define, since G is equal to minus H cof V w divided by C p, if I divide and multiply this by rho u infinity, then you will see this will be Stanton x into rho u infinity. So, rho u infinity Stanton x for V w, analogous to rho u infinity C f x by 2. That was from momentum transfer, and this is for heat transfer. Very similar formulas, which essentially implies that the analogy between heat transfer and momentum transfer through the coefficient G, the convective mass transfer coefficient. So, inert mass transfer without heat transfer. So, now we consider, now let us say in all states the temperatures are equal. So, there is no heat transfer at all, but there would be mass transfer. So, again if I consider T control volume between T state and infinity state, then there will be rate of mass flux in will be G V omega V infinity plus N w into omega V t, which is from the neighboring phase in the transfer substance state, and what will go out would be N w plus G omega V w, because the outgoing flux carries with it properties of the W state. Again if I rearrange, equate in and out, then you will get N w equal to G B m, where B m now is omega V infinity minus omega V w, omega V w minus omega V t. And for a pure liquid in the T state, omega V t will be equal to 1. And how would we evaluate omega V w? It would be evaluated from equilibrium relation at T w. Yes. So, this is what the Reynolds flow model shows even for inert mass transfer without heat transfer. Now, let us consider inert mass transfer with heat transfer. Now, in this case, let us say infinity state is not, temperature is not equal to T w and not equal to T t. Then the CV between infinity and T states will show that the rate of heat flux in will be G times Hm infinity plus Nw Hmt, and what would go out will be Nw in plus G into Hmw. Again equating, you get Nw equal to G Bmh, where Bmh is equal to Hm infinity minus Hmw divided by Hmw minus Hmt. In an inert mass transfer case, let us say air and water vapor mixture, then Hm would be omega V times enthalpy of the vapor, and omega A times, which is the mass fraction of A, into enthalpy of air, and since there are only two spaces, omega air would be written as 1 minus omega V, and enthalpy of the vapor would be Cpv T minus T ref plus lambda ref, which is the latent heat defined at T ref, and HA would have simply sensible heat Cp at T minus T ref. As you recall, if we make the Lewis number equal to 1 assumption, then Bmh would be equal to Bm, from which omega V Hw Tw relation is iteratively calculated. So, we can since Nw is equal to Gbmh and Nw is equal to Gbm. So, Bm is equal to Bmh, and we can calculate the in case the unknown Tw state and omega W states can be evaluated from the equilibrium relationship iteratively. This is exactly what we did even in Stefan flow and Couette flow models. Now, a few more interesting results. If I consider the CV between W state, infinity state, and WW state, and write, then you know this is QW, this is here I will get Nw times H Tw, this will be G times Hm infinity, and there would be G times plus Nw into Hmw. You can see now the difference between Hmw and Htw. Htw is the enthalpy of the substance which has been transferred from the neighboring phase into the phase, and therefore, if I energy in will be equal to G H m infinity plus Nw H Tw, and energy flux out will be equal to G plus Nw H Mw plus Qw and that is what I have written here. So, on the left hand side you have the fluxes going out, and on the right hand side you have the fluxes going in, and therefore, if I now rearrange these equality, then you will see Bmh would now get defined as Hm infinity minus Hmw, Hmw minus Htw plus Q wall by Nw. But you will recall we showed that Qw minus Ql, where Ql is the heat transfer in the transferred substance phase, equal to Nw Tw minus Htl. So, I can replace Qw from this relationship, and I get another expression for Bmh in terms of Q liquid divided by Nw. On the other hand, if I also consider the radiation in the transferred substance phase, then you will see that I get, if I consider radiation in the transferred substance phase, then this is the WW surface, this is the TT surface, then QL is so, QRAD is so, this is N times HMT, and here you have NW times HTL. So, I would get essentially NW HMT plus QL plus QRAD equal to NW HTL. This would be the energy balance between W and T surfaces in the presence of radiation. And then you will see that I can even replace QL divided by NW HMTL by minus HMT minus QRAD by NW. So, variety of expressions for BMH can be found when inert mass transfer with heat transfer. This is of great relevance because different expressions come handy depending on the problem at hand, the mass transfer problem at hand, as we will discover when we solve practical problems. We turn to mass transfer with heat transfer and simple chemical reaction. Now, as you know, in this case 1 kg of fuel reacts with RST kg of oxygen to produce 1 plus RST kg of product, where RST is the kilograms of oxygen to a kilogram of fuel is the stoichiometric coefficient. So, I can write between infinity and T states an equation for the fuel. This is the amount of fuel mass flux in. This is the amount of fuel mass flux in from the bottom NW, and this is the amount of fuel that will go out of the considered phase, carrying with it value of omega FUW, and all of that must equal minus RFU dot. For oxygen likewise same expression equal to minus RO2, because in the considered phase in the presence of chemical reaction both fuel and oxygen would be depleted. So, that is why I have shown these are the area, this is the volume averaged reaction rates RFU and RO2, but RO2 is equal to RST RFU, and therefore, if I divide this equation by RST and subtract from the first equation, I would again get essentially NW equal to G phi, where B phi is phi infinity minus phi W and phi W minus phi T, where phi is, as you know, is a conserved property omega FU minus omega O2 by RST. By the same reasoning, I can also form write an equation for product here, and I would get phi equal to omega FU omega product plus 1 plus RST, or omega product 1 plus RST plus omega O2 by RST. Now, we have gone over this type of material before. The important thing is, even in the presence of chemical reaction, we are able to show that NW equal to GB holds, where B is now formed from appropriate conserved property. Here we had invoked the mass conservation principle. Now, we will invoke the energy conservation principle and assume CPK equal to CPM, as we have done earlier also. Then HM will be omega k HK, CPM T minus T rep omega FU del HC, and that I can also associate del HC with omega O2 by RST. So, if I consider CV between infinity and W states, then G HM infinity plus NW HM TW would equal G plus NW HMW plus QW. If I take the second definition of HM, then again we would have NW equal to GBMH, where if I now take T ref equal to TW itself, then BMH would be HM infinity minus HMW, HMW minus HMTW plus QW NW divided by NW. That would result into CPM T infinity minus TW plus del HC omega O2 infinity minus omega O2 W divided by RST, del HC omega O2 W minus omega O2 TW divided by RST plus QW by NW. Now, of course, you can imagine, supposing I was burning a liquid fuel, it would have no oxygen. So, that would be it would have no oxygen, and therefore, that would be 0. If the liquid was at its boiling point, then no oxygen can survive there, and therefore, that would be 0, and I would get simply Cpm T infinity minus Tw del Hc omega O2 at infinity divided by Rst, and for a liquid droplet burning in air, I would readily know what omega O2 infinity is. The only thing that I now need to do is to interpret Qw. So, for a volatile fuel or transpiration cooling by combustible gas like hydrogen, omega O2W is 0, and since the transferred substance does not contain oxygen, I would get this expression. That is what I showed. If the liquid fuel is at this boiling point, Tw is equal to Tbp, then Qw minus Ql would be equal to Nw HFU, and therefore, Qw divided by Nw will be simply Cpm T infinity minus Tbp del Hc omega O2 infinity divided by Rst lambda Fu plus Ql divided by Nw. Now, for an atomized tiny droplet, we can say that there is hardly any temperature difference between W and T states. It is like saying that we have injected inside the diesel engine the liquid droplet already at its boiling point, in which case there can be no conduction heat transfer in the transferred substance phase, and therefore, you will see that with QL equal to 0 and TT equal to TBP, you will get CPT infinity minus TDP delta Hc omega 2 infinity by Rst plus lambda Fu divided by lambda Fu, and that quantity would be 0. So, you can see BMH can now be evaluated very easily, because boiling point of a liquid is known, delta Hc the heat of combustion of the fuel is known, omega O2 infinity would be typically known, and the stoichiometric coefficient in the simple chemical reaction would also be known, along with the latent heat of the fuel. So, all quantities are known, and BMH can be evaluated very, very easily. Now, when it is difficult to ascertain mass fractions of compounds in different states, it is preferred to use the conserved property n alpha equal to n alpha k omega k, n alpha k being equal to the molecular weight of alpha, the element alpha divided by molecular weight of the species in which it occurs. So, again if I do CV between infinity and T states, then an element balance would give me N W equal to G by Bm, fairly easy to see this, and Bm would be again eta alpha in infinity, W, W and T states. Many times we will find that it is much more convenient to combine different eta alpha into a new conserved property variable phi, as was shown in lecture number 32, where we considered the burning of graphite. In all cases, we now find that the Reynolds flow model results into N W equal to G B, where B is equal to psi infinity minus psi W divided by psi W minus psi T. Psi can be in only omega V, it can be element fraction eta alpha, it can be mixture enthalpy HM, or it can be an appropriately defined phi from the participating species. Any linear combination of psi's are also solutions. So, we can add any of these types of psi for our convenience. The result N W into G from the Reynolds flow model is different from the result N W G star ln 1 plus B from 1D Stefan flow model, which was essentially diffusion model, and the cured flow model. Both of them had logarithmic form, whereas here it is a G into B, it's like much more like the Ohm's law type of model. The result from the model correctly identifies BF in momentum transfer and shows that G would be equal to H Cof VW by Cp in single phase convective heat transfer. So, the Reynolds flow model result will be employed to provide the interface boundary conditions to the boundary layer flow model in the next lecture, and we will see how this can be done in the next lecture.